So in this video, we are going to see how to extend the Ito integral from simple adapted processes, the space H to 0, to the entire space H2, right? The space of adapted processes that are in L2 over the probability variable and the time variable. So we're going to do that using Ito isometry and a density argument. So we're going to pass to a limit in the L2 topology, and in order to do that, what we need is to show that H2 naught is dense in H2 for the topology, for the norm we've put on H2, right? That is literally to say we can approximate any adapted L2 process, an element of H2, by a sequence of simple adapted processes. Now the idea is that once we've proven this theorem, we will be able to define the Ito integral on all of H2 as a map that sends an H2 process to an L2 random variable just by picking a sequence of simple processes, Fn, that approximate F. And because of the Ito isometry, we have that if Fn approximates F, then Fn is a Cauchy sequence, and I of Fn by Ito isometry would have to be a Cauchy sequence, therefore it has a limit, and one can show that this limit is independent of the choice of approximating sequence Fn, and therefore I of F is well defined. Right, so really the hard part of the construction of the Ito integral, once we've defined it on simple adapted processes, is to show that the set of simple adapted processes is dense in the set H2, and then Ito isometry finishes the job. Now, this is going to be done using two different approximations, using this approximation AN and BN in definition 4.6. Let me unpack these definitions for you in a minute, but let me start with the naive idea, right? What's the naive idea? Well, we do what we would do if we were to define, say, the Riemann integral or any integration theory for that matter. We say, okay, I want to replace a function. Let's say that's the trajectory for a fixed omega, right? I'm drawing the graph of the map t goes to f of t omega here, and I want to replace it by a simple function. How do I do that? I pick a certain level of approximation here. So that's a point like ti, and that's a point ti plus 1. And then in that interval, I replace the function by something, right? I could take the value at the left-hand side, the value at the right-hand side, or maybe I can take an average of the function over that. And then the idea is, as I refine the partition, hopefully I'm going to get a convergence. Now, the problem in doing that is that if we replace a function over an entire interval by, let's say, its average on the interval, now that sounds like a good idea, because taking averages like that would mean exactly that we're approximating using a martingale decomposition, just like when we studied dyadic martingale. And we know from martingale convergence that such an approximation will nicely converge in the L2 norm. So replacing the function or the process by its average or over a time interval is a very good idea. However, it has a weakness, and the weakness is that in doing so, we're not going to get an element of H2 naught, because if you look at the average of the function on the entire interval ti to ti plus 1, then you're looking at something which is, possibly just ti plus 1 measurable, but not ti measurable. And so we're not going to have the adapted character of the process that we get through a naive, approximation by an average over intervals. So this is what we need to deal with. So let's have a look at these two approximation that we're going to use, and we're really going to need both in order to conclude. So the naive one that I described here is the approximation called Bn of f, described in definition 4.6. So you have an element of H2, you give yourself a certain partition of your interval in interval of size lengths 2 to the minus n. N is the level of approximation, which we're going to send to infinity eventually. And what you do in Bn is, on each interval, you replace the function by its average on that interval. Now you will recognize that this is exactly taking a conditional expectation with respect to the filtration generated with this by this particular the filtration that that makes all of the functions constant on such intervals measurable. So this is a very natural ID, and this is a very probabilistic ID. This is a martingale decomposition that gives you a linear combination of finitely many functions. So this looks great, but as I just mentioned, this is exactly this weakness. It's expressed here that Bn of f, if you approximate it that way, you may not end up in L2 of omega fti. These averages here, which are your coefficients, in order to be in H2 naught, you need to be adapted, so you will need these things to be fti measurable. But they're not, these objects here are not fti minus 1, measurable. They're not fti minus 1 measurable, they're purely fti measurable, and that's the problem. That's exactly why this is not in H2 naught, generally speaking. Of course, if your f is a simple, let's say if f is constant, then it is in H2 naught. But if your f is genuine, let's say between ti minus 1 and ti, it's 0 until halfway through the interval, and then it's equal to something that is only fti measurable, then that's it. You're genuinely not in H2 naught. So what you can do, and what we do in AN, is shift things. And instead of taking the average on the interval you're looking at, you take the average on the interval that came before it. And if you do that, then of course you're going to be in H2 naught, because this thing here, right? This thing here was in only L2 omega ftin. This is also L2 omega ftin. But now I'm integrating from ti to ti plus 1 instead of ti minus 1 to ti. So to be in H2 naught, I only need to be ti measurable. So the picture is like that. Compared to what we have before, I have my trajectory of my process. I look between ti and ti plus 1, and then I take the average over what happened earlier, and that is the value, let's write it in green, that I use to approximate my process on the next interval. So this looks a little weird. AN, why would you replace a function by its average before the starting point of your interval rather than the average on the interval? Well, in order to be adapted, in order to only use information coming from the past, no information coming from the future. So AN makes sense from the point of view of adaptedness. BN makes sense from the point of view of martingale approximation, and you can't conclude the proof using only one of those. So what we're going to do is we're going to use BN first to already make the process better, although not yet in H2 naught, and then we're going to apply AM to that BN. And this double approximation by AN and BN is going to give us the approximation of generic H2 processes by an H2 naught process. So the remark here is just explaining what I said. It's mentioning in point 3 here what I also said a minute ago, that you should notice that the Bn is really a conditional expectation with respect to the smallest sigma algebra that makes all the linear combination of indicator functions on the ti minus 1 to ti interval continuous, right? This is a finitely generated sigma algebra, and we've seen early in the course what the conditional expectation with respect to a finitely generated sigma algebra look like. Well, it's what you think it is, namely you construct your coefficient by averaging your process on the appropriate intervals. Right, so that's good news, because that's going to be very helpful in showing convergence of the Bn approximation. Now, the other thing you need to have a look at, and that's also going to help, is that none of these approximations can increase the L2 norm. Now, that's obvious for Bn because it's a conditional expectation, and you can just apply Jensen and you see that it cannot increase the L2 norm. It's also true by Jensen for the AN. If you compute the expectation of the AN squared, you just get the expectation of the square inside the integral, and you get that the norm, the L2 norm of A and F is smaller than the L2 norm of F. In the same way, the L2 norm of B and F is smaller than the L2 norm of F. So these approximation of F are approximation by sequences of functions that are going to be uniformly bounded in L2, thanks to that. Why is uniformly bounded in L2 so important? Well, remember that uniformly bounded in L2 implies uniform integrability. So we're going to be able to upgrade certain convergence from pointwise, from almost sure to convergence in L1, thanks to this uniform integrability. So these are all the ideas of the proof, and now we're going to have to prove two lemmas. First of all, we're going to prove lemma 4.8. We're going to prove the convergence of the B and F back to F. So Bn is a good approximation. Note that we're going to do it with an extra limitation. We're going to assume that F is not only in H2, but it's also in L infinity for technical reason. And then once we have that, we'll prove lemma 4.9 that tells us that for these elements in H2 and L infinity, if you do a double approximation, and so if you take an of BMF for any m, this is going to approximate as n goes to infinity the Bm. And then you put everything together. You want to send m to infinity, you want to send n to infinity, and you also want to remove the L infinity assumption, and that will give us the proof of theorem 4.3. Okay, so we need to do these three steps. Assuming L infinity, prove that Bn is a good approximation of F, Bn of F, then prove that An of Bm is a good approximation of Bm, and then put everything together and remove the extra L infinity assumption to prove the theorem. So let's get to it. All right, so first lemma, Bn of F tends to F in L2 norm for F in H2 intersected L infinity. So the first thing to remark, that was this remark that we had about Bn of F being of omega being a martingale. Now what we have here is that Bn of F of omega as a function of t will, okay, I should put it probably this way. So this for fixed omega as a function of t, that is a martingale. T is actually in a finite interval here, and it's a martingale that is given by conditional expectations. It has to converge, and in fact it's a martingale in the space L2 of 0t, and to make it a probability space you have to normalize your Lobeck measure. And so by Lobeck differentiation theorem, right, that we've discussed when we dealt with dialectic martingale, what do we get? We get that Bn f of omega t, and we've chosen our ti sequence, by the way, to be given by a dialectic interval, so this certainly works. This has to go to f of omega t for almost every t in 0 capital T. All right, so we have this pointwise convergence for fixed omega and almost every t. So in particular, we have pointwise convergence in omega and f. So Bn of f tends to f for almost surely as n goes to infinity. But we don't want almost sure convergence, we want convergence in L2. Now, it's tempting to say, okay, well, I know that I'm uniformly bounded in L2 of omega cross 0t, so I could use uniform integrability and get a convergence in L1. Unfortunately, I don't want just a convergence in L1, I want a convergence in L2, and that's something a little stronger. So in order to go from the almost sure convergence to a convergence in L2, I need something more. I need something like dominated convergence. Now, do we have dominated convergence? And the answer is yes, but only because we've added this assumption that f is in L infinity. So recall that Bn f of omega, for every omega, for every t, and for every n, what is it? And how large is it? it is the sum of indicator function of ti minus 1 to ti, that's scale n of t, divided by the length of this interval, which is just 2 to the minus n, and then times the integral from ti minus 1 to ti of f of omega s ds. And this sum runs from 0 to 2 to the n. Right, now I can use triangle inequality in that, and what do I get? I get that this is certainly smaller than the sum from I equals 0 to 2 to the n, and actually for any t, there's only one values of I in that sum for which what's inside the sum is non-zero, right? Because these are disjoint interval. So this is certainly smaller than the maximum over all i's of 1 upon the thing ti minus 1 to ti of, well, I might as well control f by its supremum, so the sup norm of f. So that's in L infinity of omega cross 0 t ds. And now that's a constant, and I'm taking average of a constant. I just get my constant back. So that's equal to the sup norm of f. So what have we got? We've got that Bn of f is dominated by a constant. And constants are in L1. I don't need to write that. Constants are in L1, so by dominated convergence, Bn of f squared has to converge to f squared in L1 norm. So we have that the expectation of Bn of f minus f squared. So what I have here, so f is in L2, so I'm taking an expectation of something here which is dominated. It's dominated by twice the sup norm of f, which is an integrable function. It does go to 0 almost surely. That's what we've proven first using the Lobeck differentiation theorem for every fixed value of omega, and therefore this has to go to 0 as n goes to infinity. So that's why Bn is such a good approximation, right? Because it uses Martingale's decomposition, or it uses the Lobeck differentiation theorem if you want. So as long as you can go from the almost sure convergence to the L2 convergence, then Bn is a very good way of approximating your process. And the extra assumption, which as we will see is not that hard to get rid of a posteriori in part of the proof of the theorem, under this assumption the proof goes fairly smoothly. So this is nice, but as we mentioned, Bn of f is not an element of H2 naught. So now we need to do an extra step to get an approximation in H2 naught. Let's see that now. Okay, so let's add the An approximation to the Bm approximation in order to get something in H2 naught. So to see that this would give you a good approximation in L2, what you need to realize is the following. So first of all, BMF for every omega as a function of t is constant on intervals of the form tj minus 1m to tj of m for all j running between 1 and 2 to the m. Right. That's because it's literally constructed that way. It's piecewise constant on those intervals equal to the average of the process on those intervals evaluated at the point omega in capital omega. So it's constant on those intervals. So let's have a look at those intervals. Right. So you have an interval like this, tj minus 1 of m tjm. And now if you take n greater than m, let's say strictly greater, the idea is that we're going to send n to infinity, then this interval of size 2 to the minus m times capital T can be further subdivided into intervals of side lengths 2 to the minus n times capital T, right? So you're going to have your typical ti of n to ti plus 1 of n here, right? Now, the function bmf of omega t is constant on those intervals. So what do you do when you take the an approximation on such an interval? Here, you replace the function by a constant which comes from the interval just before, right? It's the average of the process on the interval just before it. So what we have is that an of bm of f is very often going to be just plain equal to bmf of omega t. That's true whenever the interval just before the interval ti to ti plus 1 is located in the same interval tj minus 1m to tjm, because then, you know, it doesn't matter whether you take the value just before, the process is constant on the entire interval anyway. The only problem is if you look at what happens on the very first interval. Because on the very first subinterval of the interval of size length 2 to the minus mt, you have to take, so an an approximation, the average that came just before. And the average that came just before now is different, because it comes from the value of the bmf at, you know, on the interval tj minus 1 to tj that came prior to it. So what we have is what, on the other hand, we have that an of bmf of omega t, I didn't say, so this is for every omega, and this is for all t except if t is in the first interval. So for all t that is not in the union of the j's, and j runs between 1 and 2 to the m, of this first interval, which is tj minus 1 of m to tj minus 1 of m plus 2 to the minus n t. Right. On such an interval, what happens is that your an of bmf of omega t is equal to bmf of omega, and let's say if t is in such an interval, then I should say tj minus 1 m minus 2 minus nt over 2 for all t that is in an interval of the form tj minus 1m to tj minus 1m plus 2 to the minus nt. Right, because the an approximation takes the average of the function on the previous interval. So this is a problem. I don't get this equality here that obviously gives me convergence if the sequence is eventually constant on those intervals. But the idea is that those intervals are tiny, right? There's 2m of them, and they are of the size 2 to the minus n. So as I send to the minus n as I send n to infinity, the measure of these things will go to 0. So what have we got? How do I write that? So we just have that, okay, an bmf minus bmf, the L2 norm of that is smaller than the sum from j equal 1 to 2 to the m, let's square that, of the integral from tj minus 1m to tj minus 1m plus 2 minus n capital T of an bm of f of omega. I need to integrate over omega to omega comma t minus bmf of omega comma t square that dp omega dt. It really doesn't matter. I've written it in a not particularly legible manner, but that's because it doesn't matter very much, because I'm just going to control that by the supremum. So I'm going to get 2 times, okay, the 2 is squared, so it gets to 4 times the sup norm of f, because an of bm of f in sup norm is smaller than the sup of bm of f, and we've just seen in the proof of the lemma before that bm of f in sup norm is smaller than f in sup norm. So this is again where this extra assumption comes in, and then I get the sum j equal 1 to 2 to the m of those integral that sum up that are just 2 to the minus nt. So this whole thing is smaller than 4 times 2 to the m times t times the sup norm of f infinity times 2 to the minus n, and that's the whole point. Now that goes to 0 as n goes to infinity. Right, so if I take the bm approximation, then the an approximation, I send n and m to infinity, I approximate f by an element of h2 naught. So that's exactly the theorem we're trying to prove, except we've added this assumption that we now need to get rid of, that f is in an infinity. So let's see how we do that last step. Okay, so to prove our theorem now, we just need to remove this assumption and use triangle inequality appropriately to use both approximations. So how do we do that? Well, you take an f in h2, you pick a n large enough, so you give yourself an epsilon, and you pick n large enough such that if you define g of omega and t to be equal to f of omega, so let's go gn of f of omega t if f of omega t is less or equal than n, and you put it equal to n if f of omega t is greater than n. Right, so if you define that for every omega in omega and for every t in 0t, then you have that gn is in an infinity, it's smaller than capital N, and you can choose it such that gn minus f in L2 norm is smaller than epsilon, right? Because g capital N tends to f almost surely, and it's also dominated by f. So by dominated convergence, you have this approximation. So you can pick that n. I should say maybe by dominated convergence, we pick this n this way. So this is the way you prove that h2 intersected at infinity is dense in h2. And now this process here, once we have it, what do? We look at an of f minus f, and I'll send n to infinity later, so let's take an n in n for now. And I write that as an of f minus an of g, my triangle inequality, plus an of g minus g plus g minus f. No, g is a g capital N. Okay, now I know that this last term here is smaller than epsilon. That's the way I've chosen my capital N. Right, now what do I do next? I use the fact that I know that well, first of all, an is a linear map, so this is an of f minus g n. And we know that it contracts the L2 norm. That was one of the remarks we made at the beginning, a consequence of Jensen. So what I have is that this first term is also smaller than epsilon. So this has to be smaller than 2 epsilon plus an g capital N minus g capital N in L2 norm. That's a typical approximation argument. So we've reduced the problem from any f in H2 to any gn in H2 intersected L infinity. And now we do have the previous lemmas that can kick in. And so how do we use that? Well, we need to introduce the bm, right? So we're going to do that. We're going to say this is smaller than 2 epsilon plus an g capital d an of bm. So I'm going to take an n and an m, and my n is going to be greater than m. An of bm of gn minus a capital N of gn, and then plus an bm of gn minus bm of Gn that I know goes to 0, and then plus Bm of Gn. Right, so where do we go from there? We know that Bm Gn tends to 0 as m goes to infinity. So we're going to pick m. So we've chosen capital N. Now we choose little m such that an of f minus f in L2 norm is no smaller than 3 epsilon plus, and we apply the same reasoning as before here to control that by the L2 norm of Bm Gn minus Gn that we have here. So what we get is 4 epsilon plus an of Bm of Gn minus an of G capital N. Sorry, minus Bm, the middle term, of G capital M. All right, but so let's be careful here in which order we've done our approximation. We've fixed the capital N, we've given ourselves an epsilon, then we fixed the capital N. Later on, we fixed the little m. And now we have this an f minus f smaller than 4 epsilon plus this expression that involves little m and capital N. But now we're going to send n to infinity. And as we send n to infinity, we get 4 epsilon by the lemma that we've just proven about an bm minus of something minus bm of something going to 0 as n goes to infinity. And so what have we got? We've got that the limit of a and f minus f is smaller than 4 epsilon, 4 epsilon. So it is 0. When I take the limit in L2 norm. And that concludes the proof of the theorem. So this an, which is a slightly weird modification of a Riemann sum approximation. So you don't take the right rectangle or the left rectangle, you replace the value of your process in an interval by its average on the interval that came just before it. That's what an is. It's a slightly different kind of approximation, but it's exactly what we need here. It converges, this approximation converges in L2 norm and gives you an H2 naught process. And because of that, we can define the Ito integral, and the Ito integral of an element f in H2 is defined as the limit as n goes to infinity of the I of an of f for this strange approximation. And this is well defined because an of f converges to f. That's what we've just proven. So since an of f, we have that I an of f is Cauchy by the Ito isometry lemma. Right? It's the L2 norm of these things is exactly the L2 norm of A and F minus AMF. And thus converges. Right, so we know that when we do this kind of approximation, we have a sequence of integral that converges to something, and that something, that limit, is what we call the integral of an H2 process. So we've defined the Ito integral right here for any H2 process. As we go along, we're going to realize that we need an Ito integral for a slightly larger class of process, so there will be some further approximation to be done, but this is already quite a satisfying construction, right? Anything that is adapted, measurable, and quantitatively is okay, not just anything in L1, but anything that's L2 over omega and 0t is good enough for integration.